right? Now here, if we talk about this physical processes methods, so it can be written as the physical techniques. The first one, which is a physical technique. So physical technique is basically the technique which can be observed or which can be seen or which can be done physically. Here we can take an example of PVD. PVD stands for physical vapor deposition. Right? Now understood it here properly, that in bottom-up approach what we do, we go atom by atom, molecule by molecule, and same way cluster by cluster to produce the nanomaterials. Here, as we all know that we have seen the physical vapor deposition. So this PVD, okay, this PVD basically involves the condensation of the vapor phase species evaporation, either a thermal evaporation or either a E-beam evaporation. So it involves basically the condensation of the vapor phase species. So what we do, either using a thermal or E-beam, we condense that particular, we do this thing using the vapor phase species, right? Vapor phase species are condensed on a particular surface. In this manner, it creates a deposition and it creates a whole layer of the nanomaterials. It involves the generation and condensation of the vapor phase species via thermal evaporation or via sputtering or through laser ablation. We can use electron beam, we can use certain kind of thermal sources, we can use laser ablation for that. Right? It depends on the technique that which you want to use. That depends upon the sources. Okay? This technique is based in the heat produced by high energy electron beam bombardment on the material to be deposited. So we need to understand that this is the phenomenon, this is whole phenomenon, and after that just by deposition, this is basically a deposition of the material. Okay. So if we talk about laser ablation, right, laser ablation is the method of a bottom-up approach. What we are going to do in this? So in this particular method, the solid metal rod is ablated using an NdYAG laser. NdYAG laser means it contains Nd, that is neon, deuterium, ytterbium, Ag stands for argon laser. So it is NdYAG laser, which is in a very high power, in a chamber containing argon gas, right? Now, in the plasma that results from the laser ablation, metal atoms are evaporated and condensed on water-cooled substrate. We should have a water-cooled substrate for it so that they can get condensed on it, they can get placed on it. Understood it here properly. Okay. Now later the substrate is heated to remove the impurities. All the impurities will be removed at very high temperatures and the main material will be obtained here. Now here nanoparticles of gold, palladium, iron and compounds of sulfide are prepared using this particular method because it gives us very precise results. And when you get any kind of precise results, that technique will be used widely. Okay. Now, till now we have observed this physical techniques. Now we will see that what are the chemical techniques. So if you talk about the chemical techniques, it involves CVD. Okay. CVD stands for chemical vapor deposition. Here, deposition of the vapor phase of reaction species like soldier method, self-assembled monolayer method, certain can be used, right? It is basically, CVD is a chemical process used to produce high purity, high performance solid materials. And this process is often used in the semiconductor industry. They are widely used in the semiconductor industry to produce the thin films. Okay, these thin films are widely used in nano semiconductors and various. We will see the applications afterwards, but we can observe it typically. Okay, now in a typical CVD process, the wafer, that is substrate, is exposed to one or more volatile precursors which react and decompose on the substrate surface to produce the desired deposit. Okay. Now here what you need to understand is you would have a wafer which is exposed to one or more volatile precursor. Precursor means the starting material. The starting material is volatile in nature that will be exposed to, or the wafer, the below level will be exposed to the precursors, right? These precursors are volatile in nature which react or decompose on the substrate surface to produce the desired deposit. Okay, this is the substrate surface, this is the volatile precursor, they deposit on this and finally they get the desired deposit. That means they get the actual result what you want. Now we will see properties and applications of fullerenes and fullerenes. Right? From this particular part, we are going to start the properties and applications of various nanoparticles and nanomaterials, so that we get an idea that where these things are actually applied and where it is actually utilized. Okay, and why they are so much applied in the routine day-to-day life. Fine. Now, a fullerene is any molecule composed entirely of a carbon in the form of a holosphere, an ellipsoid or a tube. Right? Spherical fullerenes are also called buckyballs and cylindrical ones are called carbon nanotubes. Here various types of fullerenes are there. For an example, buckyball clusters, nanotubes and nano onions. Okay, you will see that how and why they are utilized here. Next is their properties. If we talk about the properties, the first property that came into our mind is aromaticity. Okay, researchers have been able to increase the reactivity of the fullerenes by attaching the active groups to their surfaces. And it is possible. Now, Buckminster fullerene does not exhibit super aromaticity. What is the meaning of this super aromaticity? So here, the super aromaticity, that is the electrons in the hexagonal rings do not delocalize over the whole molecule. They don't delocalize over the whole molecule. This phenomenon is known as super aromaticity. Okay. Now, let's talk about the chemistry. What is the chemistry of fullerenes and fullerols both? So, fullerenes are generally stable but not totally unreactive. They are reactive in nature but mediumly reactive in the nature. Okay. The sp3 hybridized carbon atoms are present and because of it they have a very good strength also. Right? This is about its chemistry. Now, let's move ahead to its solubility. What do you mean by their solubility? So, fullerenes are generally sparingly soluble in many solvents because it is made up of carbon. And when anything is made up of carbon, it's generally sparingly soluble. Right? Common solvents for the fullerenes include aromatics such as toluene and other like carbon disulfide. So I should say that the fullerenes can be dissolved in this particular solvent, that is carbon disulfide and toluene. They are the solvents which we can use to become or to dissolve the fullerenes into it. Okay. The next property which we will have is chirality. Chirality is one of the kind or is a type of a property It is considered as an optical property, right? Optical property can be like some fullerenes, for an example C76, C78, C80 and C84 are inherently chiral because they are D2 symmetric and have been successfully resolved. Okay. It has been observed that if you increase the number of carbons in it, their own chirality or their own properties will be changed, because generally in nanomaterials it has been observed frequently. Okay. Next property that we will have is superconductivity. Superconductivity has been reported in fullerene doped with various other alkali metals. Now it was revealed that the potassium doped C60 becomes superconducting at 18 Kelvin, 18 degree Kelvins. Okay. This is all for this session. Next we will see in our next session. Thank you.